So, welcome to the presentation, and I'm just going to jump right into starting with the architecture diagram. So, as you can see, the request starts in engine X, which is our load balancer, and it sends the request to one of 3 replicas using round robin. We were having some concurrency issues, which is why we decided to use a load balancer, and it definitely improved our performance quite a bit. Each replica is connected to RabbitMQ. Well, it's connected to Celery, which is connected to RabbitMQ, so it queues requests for asynchronous processing, and a Celery worker will pick it up from RabbitMQ. Now, each replica is also connected to the Postgres database, and you can see that the Postgres database is actually also our vector database, and we did this with the pgvector extension. Each replica is connected to min.io, which was our persistent object storage for each PDF. And they're also all connected to the sentence transformer, which the Celery workers are using to create the embeddings for the PDFs and store them. And the API replicas are using the sentence transformer to embed the queries so that each query can be compared, and we can calculate the similarity score for each query and each chunk that's being saved in the pgvector database. So here's a brief walkthrough of our code base, and I'm going to also explain a little bit about why we chose to do things how we did. So this is app.py, and it contains all of the endpoints as well as database initialization. And there's actually an argument to have database initialization separate since we're doing different replicas, but Postgres handles is fine with not exists, so it didn't end up causing any problems or race conditions. Here are all the helpers for, or not all, but some of the helpers for our endpoints. So functionality like searching chunks, etc. And here are API endpoints. Now, all of these endpoints are mainly using helpers from this file, but there are a couple that use helpers from other files, including this one. So this is post, and here's the asynchronous processing with Celery. And we do have a separate file that contains our Celery initialization as well as our Celery task. So the asynchronous task is just doing the vector processing and embedding, and then once it's done inserting to the vector database, we set the document status to ready. There's another file, which is the min.io storage file, and this file has both the initialization for min.io, which is here, and the helpers. And these helpers are used in app.py for inserting when a PDF is uploaded to the min.io persistent object storage.
So here I'm going to be showing you our system running that uses multiple services, including the Flask backend, PostgreSQL with vector support, min.io for storage, and a background worker for async processing. So to start, I'm going to create a new user account using the signup endpoint. So you can see that went through successfully. And then next, I'm going to log in to receive a JWT token, which is required for all authentication requests. And now I'm going to upload a PDF. So I'm going to take this token and put it into this search command. And as you can see, it shows that the system accepts the request and begins processing asynchronously. We can now check on this status. And as you can see, it shows the paper.pdf that we uploaded, and it is ready. And so now we're going to perform a semantic search query so that we can have the system return the most relevant chunks based on vector similarity. And so here you can see that there's several different, the top 5 are all returned. They, of course, all come from paper PDF, so they all have the same document ID because that's the only one that we've uploaded so far. They show the score. This is the similarity score, and these are the top 5 here. And then they show you the actual texts that they're pertaining to, and so that you can kind of get an idea of what the system has found to be the most similar to the query word. In this case, you could probably see earlier our query word was machine. And so now we can also upload other ones as well. We can upload other PDFs. So for example, here's another PDF that we have called just sample PDF. And when we show, when you upload that one as well, we can see that it shows PDF uploaded, processing started. And then at the same time, we can check on that as well. And as you can see, when doing that, it shows our sample PDF that was just uploaded, and of course from earlier our paper.pdf that was uploaded earlier when we started. So overall, this demonstrates the full pipeline from document upload to semantic search, including asynchronous processing, and how the request handling occurs.
So this is going to be our first load test, and this is just on one replica, so there's no load balancing going on. It's just going to the one API replica. And I'm going to start by just going to 100 users peak concurrency, and we're not actually going to get there, as you'll see. But we're going to ramp up 1 per second, and I'll start the test. And we'll take a look at the graphs and just see when the system really starts to struggle with the amount of users. As we can see, the requests are climbing steadily, which makes sense. As we get more users, we get more requests, and our system so far seems to be able to support them. And our response time is moving around a little bit, but for the most part, it's staying quite consistent. Now, we see the 95th percentile start to climb a bit, and this kind of adds up with where our previous tests were, in that around the 30 user mark with one API replica, we really start to see spikes. I'm just going to stop the test now because we can see the 95th percentile is really climbing a lot here. So I'm comfortable to say that around here is our knee, which is around the 43 user mark, and I would even say that our maximum capacity should probably be a bit lower than that. So here's the locus test with 3 replicas, and I'm actually going to adjust the ramp a little bit so that the test goes quicker, but obviously when we were testing on our own, we did more rigorous tests with slow ramp, quick ramp, etc. So we're gonna hope that with 3 replicas we get a little bit better concurrency than we did with only the 1 replica. And as we can see here, we're already at the 30 user mark, and we haven't really started to encounter any issues. Our response time is quite consistent and still quite fast, and our throughput also looks good. Now we're at the 100 user mark, and this lines up with the tests we did on our own. We start to see some spiking right around 100 users, and this is when it really starts to explode. So I would say capacity is around here, and that's right on the 100 user mark.
Now we're going to talk about key technical challenges and solutions. So during development, we face several technical challenges, especially when integrating multiple components like the vector database, asynchronous processing, and PDF parsing pipeline. One example of a big challenge was handling vector embeddings and ensuring compatibility with PostgreSQL using pgvector. We encountered errors due to mismatches between embedding formats and database types, and ultimately we debugged this by examining SQL errors and identifying that our query embeddings were being passed as Python arrays instead of proper vector types. We ultimately were able to resolve this by explicitly casting embeddings into the correct vector format and ensuring consistency between storage and query operations. Another example of a challenge was scalability. Initially, all document processing and embedding generation was done synchronously, which caused delays and could block the system. This meant that users had to wait for the entire pipeline to complete before receiving a response. We introduced RabbitMQ and Celery to move these tasks to the background workers and allowed the API to respond immediately while processing happens asynchronously. So when we run this command here to upload the document, as we can see, the status shows processing. This occurs asynchronously in the background so that users can still do other things during this time. Although the process is usually fairly quick, it can take longer for larger PDFs. Another challenge was trying to extract text from PDFs. While PyMu PDF worked well for standard documents, it would sometimes struggle with highly formatted files. And this led to inconsistent chunking, which would of course lead to poor semantic search results. And so we also discovered a bug where certain PDFs caused processing to fail, but it was very silent and hard to see when it happened. After debugging logs and testing different files, we found that these PDFs contained null bytes, which were rejected by PostgreSQL. And we ultimately fixed this by cleaning the extracted text and removing the null bytes before inserting into the database. There were also issues with Docker configuration and environment variables, incorrect credentials or missing environment variables causing startup errors. And we standardized configuration using a .env file to ensure consistency across containers. Overall, we address these challenges through systematic debugging, testing, and incremental improvements. And this process helped us build a much more robust and scalable system and let us gain experience for these sorts of engineering problems.